Hello everyone, welcome back to this course on discrete mathematics, and today we are going to deal with this topic, number theory and methods of proof. So as we have already seen some information about the propositions as well as the quantifiers, and this eventually we are going to lead into this methods of proof. Later on we will see how we can still use these quantifiers in the method of proof. But in the meantime, we will just briefly introduce about this number theory, basically the prime numbers, composite numbers, and some points on GCD and LCM. When it comes to the prime number itself, why do we go for prime numbers? Well, prime numbers has been studied by the researchers, the mathematical researchers, the mathematicians. They have been working on this prime numbers for a long time, and still the prime numbers are not well understood. There are still open research that deals with the complexity of prime numbers. When I say complexity, I try to say that these prime numbers are applicable for various areas of research, and they are trying to see and trying to map, trying to find some relationship with some of the natural things that we could see in nature. So for example, even in cryptographics, we might use these prime numbers, and they are quite effective. Prime numbers, if you could randomly generate certain prime numbers, they can be very useful for certain applications. Well, let's basically going to see about just introduction to prime numbers and composite number. Otherwise, we are just going to deal with the positive integers in this part of the chapter on number theory. Well, let's see what is the divides or divides operator. So divides operator is simply a simple notion that is indicated by a straight line, like 3 divides 12. We know 3 divides 12 4 times, right? So to specify when an integer evenly divides another integer, yes, 3 evenly divides 12 4 times. We know we can just read it as 3 divides 12. And to specify this part, we can just simply say that this means this symbol is kind of a symbol that indicates not divides. 5 does not divides 12. Okay, we can just read it as 5 does not divide 12. We can give various examples. It's just for your information, because later on we will be using these notations so that you don't get confused with what are these notations. Okay, coming to this theorem on divides operator, it's basically a algebraic operation, and we know these are some of the laws of association and other laws that we are going to consider with respect to divides operator. If A divides B and A divides C, then A divides B plus C. That's the idea. So to have an example on this, we can simply say 5 divides 25 and 5 divides 30, then 5 divides 25 plus 30. That's quite easy to understand. We have various other theorems. For example, if A divides B, then A divides B times C for all integers C. Let's see an example on this. For example, if 5 divides 25, then 5 divides 25 times C for all integers C. Similarly, we have A divides B and B divides C, then A divides C. Well, you can think of an example, right? Here it is. A divides 25, A divides 100, then 5 divides 25 divides 100, then 5 divides 100. Well, That's quite easy for us to follow. When coming back to this prime numbers, we are going to deal with this prime number for a short time now. So a positive integer p is prime if the only positive factor of p are 1 and p itself. Well, you might have studied about these prime numbers in your junior high school or even in your high school. So let's see some of the theorems related to the prime numbers as well as composite numbers. Well, if there are other factors that divides the number, we can call it as composite. And we know that 1 is not a prime, so 1 doesn't come under this category. So 1 is quite unique, it has its own class. Yes, an integer n is composite if and only if there exists an integer a such that a divides n, and a is between 1 and n. It cannot be 1, it cannot be n. If it is 1 and n, if it's only 1 and n, that is a prime number. Rather, if this a falls between 1 and n, we can call this integer as a composite. We will see some examples anyway. So the basic fundamental theorem of arithmetic is this point: every positive integer greater than 1 can be uniquely written as a prime or as a product of 2 or more primes, where the prime factors are written in order of non-decreasing size. What does it mean? Like, does it get confused with this theorem? Well, just read carefully. Every positive integer greater than 1. Okay, let's talk about integers that are greater than 1, and these can be uniquely written as a prime or as a product of 2 or more primes. So we are talking about prime or the product of 2 or more primes. So let's see an example how this can be done. We have a number which is a positive number, and this number is greater than 1, that's 100. And now we are going to write this number as a product of 2 or more prime numbers, like 100 equals 2 times 2 times 5 times 5. We know that 2 and 5 are prime numbers. 182, we can represent this by means of 2 times 7 times 13. We know that 2, 7 and 13 are prime numbers. Well, isn't it interesting that a positive integer which is greater than 1 can be represented by means of product of 2 or more primes? Well, let's see more examples. Like we have 29,820, and then again you are representing that means of 2 times 2 times 3 times 5 times 7 times 71, and these numbers are prime numbers, product of these prime numbers. Well, let's go deep down and see there are a few more relationships that we can come up with for this prime numbers, and eventually we will establish what is a composite number. Here it is, the definition. If n is a composite integer, then n has a prime divisor less than or equal to the square root of n. This is a very interesting observation. With this observation, you can actually define what is a composite number, and in fact you can also consider and see whether you can identify whether a number is prime or not. Well, let's examine. This is kind of a strong inductive proof. We have this following logics where we say n is a composite. It has a factor a such that a lies between 1 and n. In other words, a is greater than 1 but it's less than n. Thus n equals a times b, where a and b are positive integers greater than 1. And we are saying here that either a or b. If either a is less than or equal to n, the root of n, or b is less than or equal to root of n. Otherwise, a times b is greater than root of n times root of n greater than n. So let's see this observation. Thus n has a divisor not exceeding root n. So that's the idea here. The proof is quite clear, in which we have a composite number n and we have a factor. The factor is a. We start from the beginning here again. It has a factor a such that a is between 1 and n, and we thus have n equals a times b, and this again a and b are positive integers greater than 1. So now we are representing either a is less than or equal to root n, or b less than or equal to root n. Otherwise what happens? Otherwise a times b greater than root n times root n greater than n. Let's see this one in detail in the coming slides. Thus n has a divisor not exceeding root n. So we are talking about the divisors for n. So this divisor is either prime or composite. If it is a composite, if the later, then it has a prime factor. If it is a composite number, then it has a prime factor. The factors are the prime numbers. So when I say factors, I mean the divisor or the prime divisor, prime numbers. As we seen earlier, we had some numbers which divides, for example 100 is divided by product of various prime factors, right, prime numbers. In either case, n has prime factor less than root n. Let's see this example. Showing a number is prime. Show that 113 is prime. In order to show this, the only prime factors less than root of 113 is 2, 3, 5 and 7. Just take the root of n. So here n is 113. You are taking the root of n, that is root of 113, that equals 10.63, and now you are trying to see the prime factors that are less than less than 10.63. We have 2, 3, 5, 7. These are less than 10.63 because the next prime number would be 11, and 11 would be greater than 10.63. So we are just taking these numbers, and now we are going to check whether this number 113 can be divided by any of these factors, like 2. Can it be divided by 2? Can it be divided by 3? Can that be divided by 5? Or can this be divided by 7? Neither of these divides 113 evenly. So thus by this fundamental theorem of arithmetic, 113 must be prime. That's the idea. Well, let's see another example. Let's say take another number 899 and see whether can we show this is prime. Let's follow the same idea. Let's take the square root of this number. So here is the square root of the number. Okay. Root of 899 is 29.98, and you are trying to see there the numbers less than 29.98 which are prime. For example, we start with 2, then you can go on with other numbers like 3, 5, 7, 11, 13, 17 and so on. When you go on with these numbers, you come to know that 29, in fact 29 is there, and 31, in fact 31 is like greater than 29.98, because we have to find those prime numbers which is less than 29.98. That is the idea. And we come to know that 899 can be divided by 29. So if we found that, what is the conclusion that you are going to make? The conclusion is that this number is a composite number. This number is not a prime number, because prime number basically has the divisor 1 and itself. But now we have a divisor which is not 1 and itself, we have another divisor 29. So it is not a prime number. Let's move on. This are few information with respect to the unique system for the factor 899. Prime number or infinite. This is another theorem that we have to prove it. In fact, some mathematicians, they already have done this theorem, the theorem of Euclid. There are infinitely many prime numbers. That's the idea. They say that the many mathematicians have worked on this prime numbers for a long time, and they have established this theorem. There are infinitely many prime numbers. Let's see how they come with this conclusion. They use the proof of contradiction. Well, we have to establish this theorem. There are infinitely many prime numbers. So now they are going for a proof of contradiction. So what is the contradiction? That there are infinitely many prime numbers? Well, the assumption is there are a finite number of prime. That is the assumption. The finite is completely opposite of infinite. So that's why we call it as proof of contradiction. Let's start the proof. Try to list the following numbers like P1, P2 till Pn, and we say that these are the list of finite prime numbers, and you are going to consider the number q, which is P1, P2 till Pn plus 1, and then this number is not divisible by any of the listed prime. If we divide Pi into q, there would result a remainder 1. So this is one of the main part of the proof. So we have a number q, and this number q equals P1, P2 till Pn plus 1, and this number is not divisible by any of the listed prime numbers. So the listed prime numbers are P1, P2, P3 till Pn. So none of these number is used for divide the given number q. So we must conclude that q is a prime number, because it cannot be divided by other prime numbers, and there is nothing there, not among the list that you have in hand. The list that you have in hand is P1, P2, P3 till Pn, which shows that there are some number that is beyond the list that has to fit. So we have to conclude that q is a prime number, because q cannot be just divided by any of the numbers that is in the list. So this contradicts our assumption that all primes are in the list. Initially, that is our starting point. We stated that P1, P2, P3 till Pn is the list of the finite prime numbers, and then we consider q, and q is a number that is beyond that list, and we come to know that there is nothing could divide this number q. So we can conclude that q q is a prime number that is not in the list. So it goes on and on and on. Therefore, we can say that primes are infinite. Let's go further into this. The ratio of the number of prime not exceed x and x natural log x approaches 1 as x grows without bound. So that's x by natural log. We just rephrase that the number of prime number less than x is approximately x by the natural log of x. The chance of a number x being prime is 1 by log x. So that's the idea. So if you consider a 200 digit prime number, it's quite long number. The natural log 10 power 200 is approximately equal to 460, which means that the chance of a 200 digit number being prime is 1 by 460. Well, if you choose an odd number, because we know that even numbers cannot be a prime number, so if you just choose an odd number, the chances are 2 by 460, which is 1 by 230. So this is another interesting number theory that's related to prime numbers, and this proof really gives us a shortcut in which you can check and consider the existence of prime numbers even for a larger number of digits. Let's see further. Showing a number is prime or not. Consider a number 2 power 650 minus 1 is prime. We ought to show whether this is a prime number or not. So this number has about 200 digits. So there are approximately 10 power 193 prime numbers less than 2 power 650 minus 1. So by theorem, we can say that x by the log x, so where x equals 2 power 650 minus 1. So here's the question, how long that would take to test each of these prime numbers? Let's assume that your computer works quite fast and it can do 1 billion operations per second. Okay, let's see what happens. Well, if it does that fast, it would take 10 power 184 seconds to finish or to compute and check the existence of this prime number. Well, it takes 3.2 times 10 power 176 years. That's interesting, because if you consider the age of the universe itself, it's quite, our universe is, we could say, suppose assume that the universe is like 1 billion years old, or considering 4 or 5 billion years old. We are not sure when this would end if you start to compute, and we know that the existence of Earth is not that old either. We are talking about the universe. Yes, there are quicker methods to solve such problems. Let's see, there are some ways or shortcuts to do such problems. We have this algorithm called the division algorithm. Let a be an integer and d be a positive integer. Then there are unique integers q and r, with r lies between 0 and d, such that a equals d times q plus r. Let's see with some examples later. Q equals a divide d, r equals a mod d, in other words modulus. We will see some examples like the greatest common divisor, GCD. We will famously, it's called GCD, and eventually you might have studied this in your high school or in your junior high school. The greatest common divisor of two integers a and b is the largest integer d, such that d divides a and d divides b. So we can simply denote this by GCD of a comma b. Here are some examples, like GCD of 24 and 36 is 12. How do we come up with that? For 24, for example, the divisors are, you can say, starting with, if you consider 1 also, 1, 2, 3, 4, 6 and 8, 12, and 24 itself is a divisor as well. For 36, again you have 1, 2, 3, 4, okay, 6, 9 and 12, 18 and so on, right? Okay, so among this, the list that you have in hand, we can clearly see that the common divisor that is greatest to both is 12. 12 is where we have here. The greatest common divisor of both these numbers is 12. Again, when you consider 17 and 22, it's 1, nothing else is there. Again, 117, we have only 1, that is common to both. Relative primes. The two numbers are relatively prime if they don't have any common factors other than 1. So such as the one we have seen example, like 117. A and b are relatively prime if GCD of a comma b equals 1. Consider this, 25 and 39. Yeah, they are relatively prime because it has only 1 as its common divisor for both of these numbers. Let's see more on GCD. This is simple theorem or an algorithm that been developed to understand the relationship between two numbers a and b. We can write it as a equals p1 power a1, p2 power a2 till pn power an, and b equals p1 power b1, p2 power b2 till pn power bn. Example GCD, like GCD of 120 comma 500, we can express this in terms of 120 equals 2 power 3 times 5. That can be said as 2 times 3, 2 power 3 times 3 power 1 times 5 power 1. Again, 5 can be written as 2 power 2 times 5 power 3, that's equals 2 power 2 times 3 power 0 times 5 power 3. We know that anything power 0 is 1. So we are establishing this relation there. You can simply compute the GCD with this formula that we have seen. GCD of a comma b equals p1 power minimum of a1 comma b1, p2 power minimum of a2 comma b2 till pn power minimum of an comma bn. So this is an example here given for this GCD of 120 comma 500 that can be written in this fashion. Coming to the least common multiple. Okay, the least common multiple of the positive integer a and b is the smallest integer that is divisible by a and b. So now we are going to talk about the smallest integer that can be divisible by a and b. So LCM of a and b is, can be written as LCM a comma b equals p1 power the maximum of a1 b1 comma p2 power maximum a2 comma b2 until pn power maximum an comma bn. So consider this example, LCM of 10 and 25. is 50. So now we know that for example for 10, if you consider 10, the multiple of 10s are like, for example, you have 10, 20, 30, 40, 50, right? And for 25 you have say 25, 50, 75 and so on. So we know that among this list for these two numbers, 50 is the least common multiple, which is common to both 10 and 25. Again, you can consider the LCM of a larger number here, 95,256, 432. So we can use that principle to apply here, and we can in fact find it as 2 power 3 times 5 power 3 power 5 times 7 power 2, that is for 95,256, and 432 you can write it as 2 power 4 times 3 power 3. So from these expressions eventually you can see which would be your least common multiple. The basic idea behind this formula, we can use it to find the LCM. So LCM GCD theorem, here is let a and b be positive integers, then a times b equal GCD of a comma b times LCM of a comma b. So this is quite interesting. Let's see with an example here. So we saw a GCD of 10 comma 25 is 5, that's your greatest common divisor, and for the LCM of 10 and 25 is 50, and if you multiply this 5 and 50, that's equal to 10 times 25. That's interesting observation, interesting theorem that has been established. Here is again another example of GCD of 95,256 comma 432 is 216, and LCM of the same number 95,256 comma 432 equals 190,512. So well, if you multiply these two, they are equal. That's quite interesting observation. That's mathematics. Quite well. We'll talk about the pseudo random numbers. Generally speaking, about the random numbers, computers cannot purely generate a pure truly random numbers. That's why we call it as a pseudo random number, which is kind of random numbers, but at times it might start to repeat itself. Let's see an example here. Before that, we'll see a simple formula to create the pseudo random numbers. So here's an algorithm. Let's say that we start with x naught, starting with value x naught, and the modulus m, the maximum possible value, the multiplier a, that is between the value 2 and m, and we are incrementing c between 0 and m. Okay, here is the formula. The next term xn plus 1 equals a times xn plus c mod m. So we are using this formula, and let's assume that we start with x naught equals 3, m equals 9, a equals 7, and c equals 4. So now we are going to find what is x1. x1 equals 7 times x naught. So x naught is supposed to be 3, and 7 times x naught plus 4 equals 7 times 3 plus 4, that equals 25 mod 9. So this one here we are using 21 plus 4 is 25. So 25 mod 9, m value is 9. So when you see mod, I mean the modulus. So for example, when you divide 25 by 9, you get 7 as the remainder. So we take the value 7, and that 7 is going to be our x1. Now we are going for x2. So in order to find x2, in fact you are using the value of x1 there. Same thing is being repeated. Now we found x2. x2 is 8, and you are using 8 over here to find x3. Eventually you are trying to find almost all the numbers. That's when you generate this whole random number. So let's say we repeat this to a certain extent, and now we have come up with this list of random numbers, and these random numbers you can see here. The sequence is generated in which you have 3, 7, 8, 6, 1, 3, and you can see that after a certain time the whole thing has been repeated. Yeah, that's why this is called as pseudorandom. It's not a purely random, and moreover we can come up with more efficient formula. Using those efficient formulas, you can generate a sequence larger than this. Of course, that can be done. In fact, that's possible to do that as well. So in fact we have efficient algorithms to, or efficient formulas to generate such random numbers. And today the computers can in fact they can generate around 4 billion numbers before it repeats itself. That's quite a lot. In fact in most cases that's quite enough for us to deal with the random numbers. Let's see how and where these applications of random numbers, prime numbers, can be used. We know that one of the application is cryptography. So that's where we have this Julius Caesar's crypto messages. It's quite easy cryptos. We can simply use the function to encrypt the values. We have function f of p equals p plus 3 mod 26, where we have these letters for p. So p is the letter where you have a is 0, b is 1, and c is 2. Likewise until all the alphabets. So z, that is z, is 25. So you are going to decrypt. If you want to decrypt the f of 1 equals p minus 3 mod 26. So this is kind of called a substitution crypto. So you are substituting one letter with another. So let's see how this goes on. We are asked to encrypt this phrase go Cavalites. So for the word GOCAVALIERS, you have to put all those equivalent digits. For G it's 6, for O it's 14, and so on. So your full sequence is there, 6, 14, 2, 0, 21, and so on. It's there, the whole sequence. So now you are applying this Crippers, which is you are adding 3. So for the 6 becomes 9, 14 becomes 17, and so on. You just add 3 to it. So what happens? You are adding 3 and all thing is increasing by 3. That's it. Now convert back to the alphabets. So your GO becomes JR here. Initially it was GO and that becomes JR, and this part becomes here, which means that you have in fact encrypted the message. What you should do if you want to decrypt the message? Well, we already had the formula, right? Minus 3 mod 26. As if you want to decrypt this, you can just simply use J is 9 and R is 17. So you have the full sequence. You have already came up with a sequence of 9, 17, 5, 3 and so on. So now you have to apply the formula in which you have to do minus 3. Okay, so 9 has become 6, 6 has become 17. Okay, that's it. A secret message has been encrypted and now you have decrypted the message. So you are converting back and you are getting back the original number. 6 is equal to G and 4 equal to O. So you are back to where you got this whole stuff. This is the decrypted message. So if you want to send a secret message, you just send this message to your friend, and when he got the message, he can, or this is the encrypted message, right? This is the encrypted message. Once he got this message, he can decrypt by himself. You just give him the formula to decrypt it. Well, that's some of the interesting observations that we saw in today's class. So today's class we deal with the basic number theory, in which we mostly talk about prime numbers, composite numbers, GCD, LCM, pseudorandom numbers, and finally this encryption part. We just got into some of the aspects of these encryptions part, and there are a lot more informations are available. And it's good to see you today to discuss about these topics, and next time we will discuss about various methods of proofs that are available for us. So until then, goodbye.